Hello everyone. This is Lu Yi. In this video I will give a demonstration of our symbolic execution tool for Solidity. Symbolic execution explores multiple program paths by assigning symbolic instead of concrete values to variables. Consider the listed example. Here is one conditional statement, therefore, the program has two execution paths. For each path, a symbolic execution engine maintains a path condition and a symbolic memory store. A path condition is a Boolean formula that describes the conditions satisfied by the branches taken along that path. At the beginning of symbolic execution, the path condition is true, and the symbolic store only contains the assignment between symbolic variables and their respective symbols. When the conditional statement is encountered, both true and false branches are explored and the symbolic state is updated accordingly. Smart contract are computer programs running on blockchain. Solidity is a popular high-level smart contract programming language. Users interact with a smart contract by initiating transactions. For example, users can call the deposit function to trigger smart contract execution, which will deposit some money into the smart contract. In this work, we explore the application of symbolic execution to smart contracts written in Solidity. However, there are limitations on the existing techniques. On the one hand, most of the existing symbolic execution tools are on the bytecode level, which retains limited semantic information about the smart contract. On the other hand, existing source-level tools for Solidity smart contracts offer limited support for Solidity features. Some of these tools translate Solidity into an intermediate language, such as Boogie, but this will introduce discrepancies among the code translation, which will lead to false positives. In this video, we present SolSEE, a user-friendly symbolic execution engine for analyzing source code of smart contracts written in Solidity. Using the web UI of SolSEE, the user can provide one or more Solidity smart contracts and a harness function as input. The harness function specifies the sequence of function calls to be analyzed symbolically. The harness function can also be used to specify smart contract properties if the form of assertions. Given the smart contract and a harness function, SolSEE uses a Solidity compiler to generate the AST for the analyzed contracts. Then, SolSEE symbolically executes each statement by traversing the AST based on the Solidity operational semantics. The storage or memory configuration of the smart contract is encoded symbolically as Z3 types. The SMT solver is used to discharge the feasibility queries of symbolic paths and prove user-defined properties. Let's show how to use the website of SolSEE. First, enter the website URL, xyz.smartcontractsecurity.org/solsee. Now we are on the website of SolSEE. The website reused the open-source Remix IDE framework. Users can upload their local smart contract files. Here we upload a contract file assert.sol. This file contains the definitions of two smart contracts, bank and main. The bank contract has an add function. The main contract defines the harness used to verify the property of the bank contract. SolSEE considers a variable symbolic if its name is prefixed with $ symbol. These variables are, then, used to explore multiple symbolic paths of a smart contract simultaneously. In this case, the main contract has two symbolic state variables, $A and $B. Let's click the Work tab of SolSEE execution. Currently SolSEE supports smart contracts written in Solidity version 0.5. Let's click the button to trigger the symbolic execution. Then we get two relevant symbolic paths. The status of the path implies if there is any violation against the property assertion listed in the harness. We can debug each path to visualize the corresponding execution steps. For better understanding, we present the concrete values leading to those symbolic paths. Let's click the Debug button for Path 1. The Debug tab contains information about function stack, Solidity local variable and state variables as well as the sequence of executed statements. Let's walk through the execution statement by statement. For Path 1, the initial value of $A is 2 while the $B is 1. We first create a bank contract instance, and then the contract address of the bank is 0 by 1. Next we call the bank adding function. We encounter the branch condition if x greater than y. Here x is 2 while y is 1. Therefore, the true branch will be executed. The value of s will be updated and returned. Last, the assertion is checked. Definitely, the assertion is satisfied in this case. Let's come back to the Work tab of SolSEE. We can debug another path too. Similarly, let's walk through the steps. Initially, the $A is 1 while $B is 2. Let's execute the following statements. Now, we need to check that branch condition if x is greater than y. Since x is 1 and y is 2, the false branch will be executed. The value of r and s will be updated by adding x or y with 3. The r and s will be returned. Last, the assertion is checked. Definitely, the assertion is satisfied in this path too. Now we have shown the main workflow of debugging usage for SolSEE. To make a summary, the key features of SolSEE, therefore, include precise operational semantics of Solidity, support of a user-defined harness function, smart contract debugging and execution visualization enabled by a web UI. That's all. Thanks for your watching.